Welcome to this deep dive. We've tailored this one specifically for you, especially if you've got that physics background and a real interest in the deep questions about how the universe fundamentally works.
Yeah, we're diving in.
Today, our mission is kind of a comparative look. Quantum geometry dynamics, QGD versus string theory.
Right.
Now, the sources, we have some Wikipedia bits on quantum gravity, plus
Right.
detailed QGB materials. They don't explicitly set up a direct comparison.
No, not head to head.
So we'll be digging into their core concepts, their fundamental approaches to quantum gravity, trying to pull out where they really differ.
And maybe where they surprisingly echo each other, though differences seem more likely here. We've got a good overview of the big challenges in quantum gravity, including string theory basics like gravitons, extra dimensions.
Okay.
And then we have this really thorough stuff on QGD, its axiomatic goals, its basic building blocks, and what it implies for space-time gravity is quite different.
Radically different, sounds like. Our goal is really to highlight these foundational contrasts for, an audience that gets the underlying physics.
Exactly.
Okay, let's start unpacking this. Maybe the best place to begin is that huge hurdle,
Mhm.
the problem of time. It's like the classic sticking point when you try to merge quantum mechanics and general relativity.
Oh, absolutely. It's fundamental, as the Wikipedia source points out. They just treat time in completely incompatible ways.
How so? Remind us.
Well, in quantum mechanics, time is sort of external. It's
Right.
this independent background, right? A fixed stage where quantum states evolve.
Right, ticking along evenly.
Yeah, and that evolution is driven by the Hamiltonian. That's the engine, mathematically speaking.
Okay, like a metronome for the quantum world.
Kind of, yeah.
Mm-hmm.
But then you look at general relativity, and time is, well, it's part of the fabric. It's dynamic. It gets warped by gravity, by mass, and energy.
It's not just the stage, it's part of the play itself.
Precisely. And technically, there's this thing called the Hamiltonian constraint in GR, which basically vanishes. That sounds technical, but it means there isn't a straightforward engine for time evolution in the same way quantum mechanics uses it.
Ah, okay, so the math just doesn't line up easily. You can't just plug one into the other because their definitions of change over time are fundamentally different.
You got it. That's a core issue. It's a deep conceptual clash.
So how do our two main players today, string theory and QGD, handle this mess? Let's maybe touch on string theory first, acknowledging our sources are a bit more general there.
Sure. String theory, as mentioned in the Wikipedia info, swaps particles for tiny vibrating strings. That's its core idea.
Right, the little loops or strands.
And one key thing is that certain vibrations of these strings naturally look like the graviton of the particle that should carry gravity.
The quantum of gravity.
Exactly. And it often involves extra spatial dimensions curled up really small. Now, how it handles time specifically? Well, it's complex. It often relies on a background spacetime for those strings to vibrate in. Although there are ideas about spacetime itself being emergent, it doesn't necessarily solve the problem of time in a way that satisfies everyone, but it incorporates gravity quantum mechanically.
Okay, so vibrating strings, extra dimensions, gravitons popping out naturally. A very different picture. Now, QGD. How does it tackle this fundamental problem of time given its different starting point?
Yeah, QGD comes at it from a completely different angle. It's very focused on axioms, trying to build physics from the ground up, rigorously, like Hilbert wanted.
Hilbert's sixth problem, right? Axiomatize.
Exactly. And one of his core postulates is that space itself isn't continuous. It's fundamentally discrete, made of indivisible units.
Whoa, hold on. Discrete space, like
Wow.
pixels, not a smooth background.
Pretty much, yeah. They call these fundamental units of space preons. So forget smooth spacetime. At the base level, it's granular.
Okay, that's a huge departure. So no continuous stage for things to happen on.
Right. And matter in QGD is made of different fundamental particles plus preons. And these interact via something called p-gravity.
Okay, plus preons for matter, preons for space.
You got it. And they claim that our familiar smooth Euclidean space just emerges at larger scales from this discrete grid. They even have a theorem for it, the theorem on the emergence of Euclidean space.
Interesting. So we already have a major split. String theory's strings may be wiggling in some kind of continuous or emergent spacetime versus QGD's particles interacting on a fundamentally discrete spatial grid.
Yep. And that difference in the nature of space directly leads to how they view time. And this is where QGD gets really radical.
Okay.
The QGD says time is, well, it's not physical
Yeah.
at all. It's purely relational.
Not physical. Wait, what does that even mean? If it's not physical, what are clocks measuring? My watch seems pretty physical.
Yeah, it feels real, doesn't it? But according to QGD, your watch isn't measuring some fundamental flowing time. It's simply counting recurrent events, picks, cycles,
Okay.
periodic states within its own mechanism.
So it's just an event counter.
Essentially, yes. And things like time dilation clocks slowing down near massive objects or at high speeds, QGD explains that differently too.
How? If time isn't dilating.
It says it's not time itself stretching or shrinking. It's the clock's mechanism that's intrinsically affected by gravity or speed, interacting differently with that underlying preonic structure. The clock literally runs slower because its internal processes are changing.
Okay. But does that match observations, like GPS satellites needing adjustments?
That's the claim. QGD asserts that even with this completely different conceptual basis, time is non-physical, clocks just counting its predictions for these relativistic effects perfectly match the observations and the mathematics of special and general relativity.
Wow. Okay. Same numbers, radically different interpretation of what the numbers mean. Time itself isn't the variable. The clock's workings are.
That's the QGD picture, a huge contrast to both GR's dynamic time and quantum mechanics background time.
Definitely a core difference. All right, let's talk gravity itself. We know string theory gives us the graviton from string vibrations.
Correct. Massless, spin-2 particle pops right out of the string spectrum. It's a force carrier for gravity in that framework.
Straightforward enough, conceptually at least.
Okay.
And QGD. How does gravity work with these plus preons on a discrete grid?
Well, it arises from interactions between the preons. There's that fundamental pre-gravity
What the-
between the matter preons, the plus ones, which is attractive.
Okay.
But then there's also n-gravity, which acts between all preons, both plus and
Yeah.
p. And this n-gravity is interesting. It could be attractive or repulsive, depending on the distance. There's a specific threshold distance, they call it d, where it switches.
Attractive and repulsive gravity, depending on scale. That's unusual.
It is. But maybe the most startling claim about gravity in QGD is its speed.
Speed. Don't we know gravity travels at the speed of light? We've seen gravitational waves.
Exactly. General relativity predicts speed of light propagation, and observations like GW 17876 seem to confirm it beautifully. But QGD predicts that the fundamental gravitational interaction is instantaneous.
Instantaneous, but then throw it. The waves. LIGO, Virgo, how can they possibly square that? That seems like a direct contradiction of experimental evidence.
They don't square it, they reinterpret the evidence. QGD addresses GW 170876 directly, yes.
Yeah.
Their explanation is that the signals detected weren't gravitational waves propagating through spacetime in the GR sense.
So what were they then, according to QGD?
They propose it was an electromagnetic phenomenon. Essentially, the merging black holes or neutron stars caused a massive disturbance of polarization in the underlying preonic field, the discrete space itself, generating electromagnetic signals that mimic what we interpreted as gravitational waves.
Okay. That's a bold reinterpretation. So they're saying we detected something, but we fundamentally misunderstood what it was.
That seems to be their position. It implies gravity itself, the fundamental force between preons, acts instantly. But large-scale disturbances involving matter might generate speed-of-light electromagnetic signals in the preonic medium. It's a very different physical picture.
Presumably a testable one. If it's electromagnetic, it might have different properties or correlations.
Presumably, yes.
Yeah.
That's a key point. It leads to potentially different observational signatures than the standard GR interpretation. A major, major divergence.
Absolutely. This also touches on the math they use. You mentioned QGD leans heavily on discreteness. Does that extend beyond just space?
It does. QGD argues that if physical reality is discrete at its base, then the mathematics describing it should also be fundamentally discrete. Meaning concepts like infinity or the continuum of real numbers, things we use constantly in physics, are just useful approximations, mathematical tools, not reflections of the deepest physical reality. No true infinities, no perfectly smooth lines in nature at the bottom level.
Okay, so discrete math for a discrete reality.
That's the idea. Which, again, contrasts sharply with string theory. String theory relies heavily on advanced, continuous mathematics calculus, differential geometry, complex numbers, continuous manifolds for spacetime.
Yeah, the math in string theory is notoriously complex and, well, continuous.
So we have a clash even in the mathematical language used to describe the universe. Discrete versus continuous, right down to the foundations.
It really feels like QGD is trying to rebuild physics from scratch, axiom by axiom, challenging assumptions we barely even think to question, like continuity.
That seems to be the ambition. It's less about tweaking existing theories and more about proposing entirely new foundations.
Now, both theories are ultimately aiming for some kind of unification, right? bringing gravity under the same roof as the other forces, bridging GR and quantum mechanics. How do their approaches to unification differ?
Well, string theory is explicitly an attempt at a theory of everything, unifying all forces and particles via string vibrations. It tries to extend quantum field theory principles to include gravity.
Okay, the traditional grand unification goal.
Yes, QGD's take is, again, different. Based on its axiomatic analysis, it concludes that unifying quantum mechanics and general relativity, as they are currently formulated, is actually mathematically impossible.
Impossible. Not just hard, but impossible.
That's their claim, because the starting axioms, particularly concerning time and space, continuous versus discrete, implicit assumptions, the role of the Hamiltonian, are mutually exclusive. You can't logically combine both sets as they stand.
So QGD isn't trying to merge QM and GR directly.
Not directly, no. Instead, it proposes its own set of axioms, discrete preons, relational time, specific interactions from which it believes the phenomena described by both QM and GR can be derived within one consistent framework. It aims to replace, not just reconcile.
Replace them with something more fundamental that reproduces their results where they work, but avoids the contradictions.
That's the goal. Build everything from those few core axioms about plus and preons and their interactions. String theory, meanwhile, works more within the lineage of quantum field theory, adding new ingredients like strings and extra dimensions to incorporate gravity.
Two very different strategies for tackling the same big problem. Finally, and this is crucial for you listening with that physics background, testable predictions. Does QGD offer ways we could actually check if it's right? Ways that differ from string theory or GR?
Yes, they emphasize this. The goal is definitely to derive predictions that are distinct. The gravitational wave interpretation is a prime example.
Right, looking for electromagnetic signatures instead of pure gravitational ones.
Exactly. If their interpretation is correct, future observations of merging events might show specific electromagnetic characteristics that GR wouldn't predict. The QGD materials suggest they're actively working on identifying other such unique, experimentally verifiable consequences of their framework.
Okay. Crucial for any theory wanting to move beyond mathematical elegance into physical reality.
Absolutely. It has to make contact with the experiment eventually.
This has been, wow, a really deep dive into some radically different ideas. Let's try to quickly recap the main contrasts we've pulled out between QGD and string theory, keeping our physics-savvy listener in mind.
Okay. Big picture. They start from fundamentally different places. QGD posits a discrete reality space made of preons, matter from plus preons. Time is not physical, just relational counting. Gravity involves attractive repulsive forces between preons, acting instantaneously at the base level. Mathematics itself is seen as fundamentally discrete.
Right. Discrete, relational, instantaneous gravity, discrete math, and string theory.
String theory starts with fundamental vibrating strings. Gravity comes from a specific vibration mode, the graviton. It usually lives in a continuous spacetime, often with extra dimensions. Time is typically treated more conventionally, though its exact quantum nature is complex. It uses sophisticated continuous mathematics.
Continuous spacetime, vibrating strings, gravitons, continuous math. Got it. So
Yeah.
while both are trying to figure out quantum gravity,
Their core assumptions about what space is, what time is, what matter is, and even what math is fundamentally are just worlds apart.
worlds apart, yeah. It wasn't a direct comparison in the sources, but digging into them really highlights these profound conceptual divides.
It really does.
Mm.
And for you listening, especially with your physics background, seeing these starkly different paths, QGD's bottom-up axiomatic rebuild versus string theory's extension of existing frameworks, it just underlines how big the challenge of quantum gravity is. We still don't know the right fundamental assumptions.
The very nature of reality at its smallest scales is genuinely up for grabs.
Completely. Which leads to a final thought.
Yeah, let's leave our listener with this. Considering these incredibly different pictures, QGD's pixelated universe with no flow of time versus string theory's vibrating strands in perhaps higher dimensions, what fundamental piece of the puzzle do you think is the most crucial? Where is the key lie to finally unlocking that complete theory of quantum gravity?
Is it the nature of space, the nature of time, the fundamental constituents, or something else entirely?
Something to ponder. It's why this field is so challenging and so exciting. Thanks for joining us on this deep dive.